Okay, we're on. So 5.1, we've been jumping around. We did the triangle stuff ahead of time so that we could have something nice, simple, cookie cutter, um, which is not what we're getting into now. So we're going to be looking at identities. Today we're going to do a couple things. I'm going to show you the first half of our identity sheet. If you've got your identity sheet out and you look, today we are going to cover up through and including odd and even. And this will be, you will eventually take a memorization quiz over this stuff. So you are going to memorize all of these identities. Now, the nice thing is that for a lot of them, if you know like one of them in the category, then you know them all. There's a link between them. And just to put your mind at ease, when we do take this quiz, what it's going to look like is it'll be like the identity sheet, but it'll have some of these things blanked out, and you'll just fill in the box that's blanking it out. So there'll be one on there that says sine squared plus empty box equals 1, and you just need to know that cosine squared goes inside of that box. So it's not like you're going to have to come up with all of these from scratch, but you kind of need to know how they're related to one another. So first half, we are going to go through and introduce the first half of this, and I'm going to focus on why these things are as they are. And then in the second half of class today, we'll actually start using some of these identities to simplify some expressions. So does yours, I just noticed this, does yours have that same typo there? This is missing something. Yeah? This should actually say cotangent of negative theta equals negative cotangent theta. I must have accidentally deleted some piece of that. Not sure how that happened, but I'll have to go back and fix that file. Okay, well, here we go. So these identities, for now, I just want you to trust that these identities exist, and that there is a good reason for us to use them. That reason, well, I should just tell you what the reason is. The reason is we're going to practice taking expressions that have sines and cosines and the other trig functions and changing the way they look. For today, we're going to focus on simplifying them, taking something that's complex and trying to turn it into something simpler. And you guys all know the value in mathematics of taking something complex and finding a simpler way to put it. It makes solving easier, it makes analysis easier. We do a lot of that in math. Next year in calculus, you're going to be working with these things called derivatives and integrals, and there are some things that are really easy to take an integral or a derivative of, and there's some things that are really, really time-consuming and difficult to do those same two things with. So a lot of the work that goes on in calculus is, I've got this thing and I'm looking at it like, oh my gosh, I do not want to take the integral of this thing. It's going to take me half an hour. Like literally to go all through all the steps to do it. But if I can be clever and take that same problem and change the way it looks a little bit, modify it so it looks a little bit different, then it could be like 30-second problem. Right? So the whole idea, what we're going to be practicing is going to be useful to you in the future because this comes up a lot in math where you're like, geez, this thing looks like a mess, but I feel like I have a tool that can change the way that it looks and turn it into something else that might not be so overbearing to deal with. So that's kind of the point of this. So we're going to start off with kind of the fundamental identities that we're going to be using the most. So there are 6 reciprocal identities. I've got the first one up here. You guys know the other 5. We at least know the other 2 main ones. This is cosecant. What is the secant of theta? You guys already know this. It's 1 over cosine. And the cotangent of theta is 1 over tangent. There are 3 others. They're just reverses of these. So sine theta is the reciprocal of cosecant. And I'll let you write the other 3 down. So these are called the reciprocal identities. We will end up using these a lot when we approach an expression that has secants and cosecants and tangents or cotangents, and we'll use it to try and turn everything into sines and cosines. All right, I don't have too much to say about the reciprocal identities. They are kind of basic definitions of secant, cosecant, and cotangent. Quotient identities, we've been using this first one for a while. Tangent is equal to sine over cosine. You should know that forwards and backwards at this point. And then the other one is the cotangent one. Do you know the cotangent one? It also has sine and cosine in it. What is it? It's cosine over sine. It's just the reciprocal. Oh, our next memorization quiz is on Friday. You guys been practicing? What's the cosine of 45? Without looking at your sheet. Cosine of 45. Nope. Same as the sine of 45. Root 2 over 2. What's the tangent of 60? It's root 3. Yep. What's the tangent of 30? 1 over root 3, but I'd rather you write it as root 3 over 3, though. Make sure you rationalize it. Sine of 30. Oh, we're going to need to practice this. Okay. Sine of 30, no. That's cosine of 30. Cosine of 30 is root 3 over 2. Sine of 30 is 1/2. And how about cosine of 90? The last one we'll do. It's 1 or 0. Good call. Or undefined. But no, it's only tangent that's undefined. Which one's cosine? 0. Okay. All right. Anyways, enough of that. Moving right along. This next one, there's a bit of a typo here. There should be a parentheses, and this should be separated a little bit more. I've already fixed that for next year. These next ones are called the Pythagorean identities, and they are super important. We use these all the time. They pop up. These are awesome when they come up too, because they usually allow you to turn something super complicated into something much, much simpler. And they are based off of the Pythagorean theorem. So if you think about your reference triangle inside of a unit circle, we know this is a unit circle, right? Because it's got a radius of 1. And we think about our point here. By now, this should be second nature to us also. Do you guys all know that the x-coordinate of any point on the unit circle is cosine and the y-coordinate is sine? That means that we could pull this right triangle out. The bottom would be cosine theta. The side would be sine theta. The hypotenuse would be 1. And we could apply Pythagorean theorem to it, which would say that the sine of theta squared plus the cosine of theta squared is equal to 1 squared. And that is the primary Pythagorean identity. We actually write it without the parentheses, like this. Now this makes me a little bit unhappy because someone at some point decided it was okay if the entirety of sine theta was being squared, that it was okay for us to put that square onto the sine rather than have parentheses around everything. But this is inconsistent because remember when we did inverse sine and I said absolutely that little thing that looks like an exponent is not an exponent, the little -1, right? So this kind of bugs me a little bit, whoever decided to do this. If you ever see a sign and it's got an exponent on the actual sign, as long as that exponent is not -1, it is an exponent. So sine to the 4th of theta means sine of theta in a parentheses with the 4th on the outside. But sine -1 of theta does not mean sine in a parentheses with a -1 on the outside. It means take the inverse. So that's a little bothersome to me. But anyways, I'll get over it. There are 3 of these. There's actually a lot more if we count the different modifications we can do, which we'll talk about in a second. But there are 3 of these. I don't have the other 2 memorized because I know how to get the other 2 really, really quickly. So from this. So here's what I'm going to do. I'm going to rewrite this, and I'm going to abbreviate a little bit. Sine squared plus cosine squared is equal to 1. I'm going to write it twice. And I can get my other 2 Pythagorean identities by just taking this primary one and dividing everything strategically by either sine or cosine. If I divide it by sine squared, what do I end up getting? What is sine squared over sine squared? 1. Plus, what is cosine squared over sine squared? Cosine over sine is that tangent or cotangent? That's cotangent. Cotangent, but it would be cotangent squared, agreed? And what is 1 over sine squared? 1 over sine squared, is that secant or cosecant? Cosecant. So there's one of my other 2. So there's 1 plus cotangent squared theta is equal to cosecant squared theta. I can come up with the other one by going back to the primary one that I have memorized, and you're going to use this one the most. And I'm going to divide this time everything by cosine squared. And then I'll simplify. Sine over cosine is tangent. Cosine over cosine is 1, and 1 over cosine is secant. So there's my other 2. Tangent squared theta plus 1 equals secant squared theta. This might be the year that I actually memorize these 2 things. I don't know. I've been teaching pre-calc for like 12 years at this point, and I still don't have those 2 memorized. And it's because I am super comfortable that if I need them, I can do this like in the margin of my paper in like 10 seconds and figure out what it is. All right, so those are the 3 Pythagorean identities, but we can also use any variation on those. So let me give you an example of a variation for this one. A common variation would be that sine squared theta is equal to 1 minus cosine squared theta. Do you see how I could take that top one and do a little bit of algebraic manipulation and come up with the bottom one? So I need you to know that this exists, but I also need you to know that adding or subtracting anything from both sides will give you another thing that also could be potentially useful. So 1 minus sine squared is equal to cosine squared. Cosine squared, yeah, so moving either of these 2 things over. In this one, sometimes you'll see cosecant squared minus 1 or cosecant squared minus cotangent squared. So you should be comfortable manipulating these to come up with other versions of these as well. And so in that light, there's probably like 9 different Pythagorean identities that we'll be using. But as long as you've got these 3 main ones down, then you should be good to go. All right, let's talk about the cofunction identities. Cofunction identities are ones that allow you to relate a function to its cofunction. An example of a function and cofunction relationship would be sine and cosine. Like, so if you can take the thing and stick a CO in front of it, then that's a cofunction. What's the cofunction of secant? Cosecant. What's the cofunction of tangent? Cotangent. If there was another trig function called, I don't know, samdant, what would the cofunction be? Cosamdant. Okay, so it's just co in front of the thing. So let's see if we can work this out. I want to show you why this works. If I asked you to write a sine equation, and I want you to just think in SOHCAHTOA, basic geometry level trigonometry, could you write me an equation that would have theta and h and y in it? See if I challenge you to write me an equation. SOHCAHTOA equation. I'll give you a hint. The angle always goes inside of the sign. Pick up your pencil and put the angle in here. It's theta. It's theta. It's going to go right here. And then draw me a fraction bar and put some h's and y's in the right spot in that fraction bar. You got it? Sine is equal to opposite over hypotenuse. Did you put y over h here? Nice. All right. Ooh, I said y over h, didn't I? And then a different thing came out of my hand. Y over h. There we go. All right, if I wanted to repeat this with cosine, and I don't have anything for this side right here, we can still do it with only introducing one more thing, the number 90. I would need to use this angle instead if I wanted to do a cosine equation, agreed? Because this is the angle that has adjacent and hypotenuse, agreed? So tell me what this angle is here. If this is theta, what would this angle be? No, they can't both be theta. What do all the angles in a triangle add up to? 180. If I take out that 90-degree angle, how much do those two angles add up to? 90. So if this is theta, then this must be what? 90 minus theta. Thank you. 90 minus theta. Agreed? If that's 20 and I asked you to find this, you would do 90 minus 20 to get 70. If this was 10, you would do 90 minus 10 to get 80. So 90 minus, okay, write me an equation with 90 minus theta in there. This time we're doing cosine, so it's adjacent over hypotenuse. What do we got? Oh my goodness, it's the same thing. It's the same thing. It's y over h again, isn't it? You know what that means? That means for any angle ever, the sine of theta is equal to the cosine of 90 minus theta. That's just 90. 90 minus theta. When we write our cofunction identities down, though, we will be using radians instead of degrees. So here's your first one. The sine of any angle theta is equal to the cosine of pi over 2 minus theta. There are 6 of these because we could do it that way, or we could go cosine theta is equal to the sine of pi over 2 minus theta. Could you please find me the other 4? I'll give you a hint. I'll give you the starter, the stem for each of them. Secant theta is equal to something, and tangent theta is equal to something. All right, so those are useful when you end up with an expression that's got pi over 2 minus theta someplace in it, inside of a trig function. Okay, any questions so far? You guys are doing awesome. We only have one more category to go, and then we'll start looking at some problems. Do you have questions about any of the other ones, or? I wasn't planning on writing them down. Yeah, tangent theta is equal to cotangent of pi over 2 minus theta. So it's just the cofunction of an angle is always equal to the function, but the same angle, but pi over 2 minus that angle. All good? And then tangent would look the same, just, yeah, cotangent would be the same idea. And these are all on your sheet. The next one, before you flip the page over, the next one has to do with odd and even functions, and this might be where I actually get everybody across the line on odd and even functions. It's come up like 5 times this year. Do you guys remember the algebraic definition of odd and even functions? You need to, okay? You need to. F of negative x is equal to something, and for even functions, and f of negative x is equal to something else for odd functions. Who remembers this one? F of negative x is equal to, say again? Nope. Try again. I think I heard someone say it. I was saying nope to negative f of x. That's not right. Just f of x, yes. It's equal to f of x. These are the ones, if I put a negative version of x in for x, I'm just going to end up getting the exact same function. And then for odd functions, if I put a negative in for x, I'm going to get the opposite, the negative of f of x. You guys are going to remember this after this because now it's actually useful to you. Because what we're going to see is we're going to be dealing with some equations, and really, I need you to know why this, I need you to be able to at least answer the why question, but check this out. If you have an even function, and you find that there's a negative x inside of your function, you can just drop it. You can just leave that negative off of it. You've just simplified that thing by taking that negative out of the inside and just tossing it away. Okay, and then if you have an odd function with a negative x on the inside, you can bring the negative to the outside, which often simplifies things because we don't usually like having negatives on the inside of functions when we're dealing with it. So moving forward, you're going to actually be able to use these things to do useful things. And I hope that you will remember them going forward and why. So I don't actually have the even and odd identities. There's 6 of them. I don't have them memorized. I just know which of the functions are even and which ones are odd, and I'm able to apply this really quickly to it. So let's figure out which ones are even and which ones are odd. So notice that I have a couple of angles here, and they're the same angle, but they're opposites. So this is the cosine of theta, and this is the cosine of negative theta. Okay. So I want you to focus your attention first on the x-coordinate of these 2 points. That would be my cosine theta and my cosine of negative theta. And what do you know about the x-coordinate of these 2 points? If the angle magnitude is the same, what will be true about the x-coordinates for these 2 points? They're exactly equal to each other. They are the same as each other. This x-coordinate and this x-coordinate are equal, which means what? If I've got the cosine of negative x and the cosine of x and they're equal to each other, that means that this function is even. Cosine is an even function. So there we go. What that means is if I ever am working and I end up with the cosine of negative x, I'm allowed to just drop the negative. And if anybody asks me why, I'm going to tell them because cosine's even. And for even functions, the function of the opposite is equal to the function of the regular one. Now focus with me on the sine theta and sine negative theta. That would be the y coordinates for these 2 points. Would the y coordinates be exactly the same for these 2 points? They would not. What would be the difference? One's positive and one's negative. Other than that, it should be the same, right? So these are not equal to each other. They are opposites, which means that that sine is an odd function. If I knew what f of negative x was, I could just take the opposite sign of it to get f of x, and vice versa. So sine is odd, and that's super useful to us because if we ever run into sine of negative x, we're just going to turn it into negative sine x. We're going to bring that x to the outside. Tangent goes with sine, tangent sine over cosine, and when you do a odd function divided by an even function, you're always going to get an odd function. That seems to me like it was in a true-false question on the practice test for chapter 1. I know we talked about it at some point. The other 3 come from these. So cosine is even and secant is also even. So secant of the opposite of x is equal to the secant of x. And then sine goes with cosecant, so same idea. With sine, it's the opposite of cosecant x. Tangent and cotangent match up as well. So I don't have these 6 memorized. I know the definition of odd and even functions because I have used them hundreds, if not thousands of times. And then I just have memorized that cosine is even and the other 2 are odd. All right. And there are our identities. These are called the fundamental trigonometric identities because everything on your sheet after these can be built by using combinations of these ones. So we'll come back and we'll look at some difference in multiple angles and all that stuff later on in some further sections, but for right now we're just going to practice utilizing these ones. I need to tell you something about this sheet. I mentioned earlier that you were going to be memorizing these, and I know that when you do it, it's going to be one of those, like, I'll tell you it's going to be next Thursday, and you guys are going to, like, have it memorized Wednesday night, and you're going to take your quiz on Thursday, and you're going to memory dump it. I know that it's not going to stick around in there forever, and that's fine. I don't expect that most people will have all of these things actually memorized. In fact, on the test, I've already told you you'll be able to use this on the test. So why do I need you to memorize it if you're allowed to use this thing on the test? The reason is the more familiar you are with all the identities that are on this sheet, the better you're going to be when it comes time to doing proofs. One of the things that really holds my students up when they're doing proofs is they get to a certain step and they're like, okay, I'm going to need to use an identity. And they look at this sheet and they have to look through every single identity in this sheet to try and find something that's going to work for them. Somebody who's good at proofs, who has familiarized themselves with this, I might not know this identity, for example, but when I see tangent squared plus 1 come up in a proof, like, I know where to look to get this thing. I know that sounds like a Pythagorean identity, and I know where it is on my sheet, and I can get to it quickly. It's kind of like I told you, Mr. Skaggs has the analogy of a new mechanic working on a truck. Okay, like you're working on an engine's over here, tool chest is over there. If every time you need a tool, you've got to walk from here over the tool chest and look through every single drawer, pull this one out, come over here and try it, nope, go over, put it back, pull something out, come over here and try it, nope, put it back. It's going to take you forever, and a new mechanic is going to take forever to fix something. Somebody who's a pro, who's been good at this, is going to be able to look at that engine and say, okay, I need this size hex bolt. It's either one of these 2 size hex bolts for this bolt to come out, or hex socket. So they can walk over and they can grab the 2 things that they think it is without having to barely even look at it, check it out and see which one fits, and they're off and running. That needs to be where you need to get with these things. I don't need you to actually have them memorized, but when a situation comes up where you could use one of these things, I need you to be familiar enough that you can just know intuitively, like, oh, that looks like I'm going to be using an odd even, or that's going to be one of the cofunction things. Ways that you're going to get there, I'm going to suggest a couple things as we're doing our work today. The big one would be have this out in front of you, but try to visualize it before you look at this thing and just start pouring it over. See if you can pinpoint at least what category may be useful. When you start, you're going to have no idea, but just make a guess. Like, that looks like it might be a quotient. And then as you get better at it, try and name the category as well. So that said, we're going to get into some examples of this. And I do have some rules, some pretty strict rules about how you're going to show your work for this. And these are designed specifically, you're going to need your notebook, by the way, for what's coming next. These are designed specifically to help you with the stuff that's coming up with the proofs. So when you're working these, I'm going to give you, the problem's going to give you an expression, not an equation, but an expression that has some trig stuff in it. And your job is going to be to simplify it as much as possible. Try and get it down to a single trig function. The rule is I need you to show all of your steps. So this is kind of like proof in geometry. The point is not to get to the answer as fast as possible. The point is to communicate clearly how you got from one step to another. So show your steps. You may only do one identity category per step. When I say that, I mean if you've got both a cosecant and a tangent in your expression, you can either do reciprocal or quotient in the first step. You may not replace both things with a reciprocal or quotient in the same step. However, if you've got cosecant and secant in your expression, I'm okay with you turning the cosecant into 1 over sine and the secant into 1 over cosine in the same step because it is the same category of identity. Okay. And then the last thing is going to be the format, but I'll show you what I want for format as we go through our examples today. So here we go. Label something at the top of your notes here. This is from Lesson 4, Section 5.1. And we're just going to go through and do some examples. So example 1. So cotangent x sine x. So let's say that was written in the book. Here is what I would want you to write on your page. This is what your work is going to look like. You're going to write number 1. You're going to write the original expression down. Many of you have developed or gotten back into the bad habit of not even writing the original problems down. That's not going to fly in this chapter. That's my original expression. It's going to be followed by an equal sign, and then all of my work is going to be in a vertical column going down from this. Every step that I do is going to have another equal sign because it's going to be equal to the thing above it. And I'm going to keep going down the page until I get to the simplest thing I can possibly make out of this. Move if you need to, okay? I appreciate that you guys are talking, and I'm assuming it's probably like, what am I going to do first here? But for right now, just go ahead and separate. Thank you. All right, cotangent x sine x. I want to simplify this thing. What am I going to do? I want to point out a couple things. This is on the back side of your identity sheet. And these strategies go with trigonometric proofs, which we have not started yet, but these 5 dots that I've colored in here are all applicable to simplifying as well. The only one that's really not applicable is the try working from the other side, because we don't have another side right now. We're just dealing with expressions. For right now, I would say for what we're doing, I really want you guys to focus on this one. If you get stuck and you're not sure what to do, try and put everything in terms of sine and cosine. Every trig function, all the other 4 trig functions can all be written in terms of sine and cosine. Secant is 1 over cosine. Cotangent is cosine over sine. So if you get stuck and you're not sure what to do, at least try and do that. Some other things that are going to come up fairly frequently would be getting a common denominator, factoring, and then our difference of squares and square of a binomial rules, which we'll practice at the end of our lesson today. So looking at this, if I'm not sure what to do, I'm thinking this is a sine or why don't we turn this into a sine and cosine? Cotangent, how can we turn cotangent into sines and cosines? What category of identity should I be looking for on my sheet? If I want to turn cotangent into sines and cosines, I'm looking at quotient identities. The cotangent is equal to cosine over sine. Let's make that change first. So in my next step right off to the side here, I'm going to have cotangent will turn into sine x over cosine x. Oh, wait. I did that upside down, didn't I? Cotangent is cosine over sine, right? Yes? Help me out, guys. You've got the sheet in front of you. Yes, cosine x over sine x. And then I have not done it. I'm not doing anything with this sine x that's over here right now. All right, cool. That looks great to me. Anybody think about canceling as sine x's? Right? We're dividing by sine x, we're multiplying by sine x. Those can cancel. Now, do not cross them out. You're going to leave them there. You're just going to write down the result. So equals, that's just cosine x. And once you get it down to the point where it's a single trig function, we're going to call that good. That's as simple as that's going to get. So that's it. We're done with our first example. Hooray, that wasn't too bad. What do you guys think? Wasn't that fun? All right, let's do another one. Let's do number 2. I'm just going to jump straight to my work for this one because the problem's built into this. So number 2 is cosecant x times sine of pi minus x. Pi over 2 minus x. Sorry, I had something covering up half of that equation, or expression rather. Pi over 2 minus x, what does that make you think of? Which category of trig identities has the pi over 2 minus x's in it? Those are our cofunction identities. So let's use one of those. We can turn sine into its cofunction. The cofunction of sine is cosine. So we could just rewrite this as cosecant x. That didn't change. Sine of pi over 2 minus x is equal to the cosine of x. You're going to hear me ask this question a lot. Which category of identity does this make you think of? One thing that you could do to help get yourself more familiar with the sheet is to try and think about that again as you're working. When you're looking at this, try and think about the name of the category and where it is on your sheet. And then I had a student last year who actually, this is not required. I had a student last year who started writing the name of the category next to each step. The nice thing is, in trigonometric proofs, I'm not going to make you give reasons for anything. Like in geometry, remember how you always had to have a statement and a reason? In our proofs, we don't have to do that. Okay, we just have to use one of the theorems or one of the identities. But this person was going a step ahead, and they were writing next to each step what they were doing. And it helped them, I guess, to go back when they were looking at it and studying later to say, oh, I see, this was my cofunction that allowed me to change this sine of pi over 2 minus x into cosine x. That person did super well on proofs last year. I don't know if it was because they chose to do this for every step or if they would have done awesome on it either way. But something that you might consider if you start feeling like you're struggling with this stuff. So I think we could probably take this further than this. I'm not 100% sure, but let's try. What else could we do? I'm going to leave this cosine x alone for right now, but this cosecant, I feel like we could change that into something. What do you think? 1 over sine x, what category is that? Reciprocal, you're thinking reciprocal? Yeah, let's try it. Let's see what happens. If we change this into 1 over sine x, we've got 1 over sine x times cosine x. That, if I were writing this out, I could say this was the reciprocal category. Is that better? It looks more complicated to me right now, but we could multiply these two fractions, or these two, they are technically two fractions, right? We could multiply them together. And that would give us cosine x over sine x. And I kind of like that because why? What is cosine x over sine x? That's cotangent. And I think that's as simple as we're going to get this. So what do we do here? We just multiplied them. I'm just going to write simplify. And then cotangent, we used a quotient identity. Bless you. All right, let's keep going. Number 3. Oh, I love this one. Number 3 is cosecant squared x minus 1 over cosine squared x. As soon as I see those squares, I start thinking about a particular category of identities, just because I've seen so many of these. Which one does it make you think of? Of the top half of that sheet, where are you seeing squares? Pythagorean. I think we're going to use a Pythagorean identity in this one. I'm going to see if I can, I'm looking at the top here, and I'm going to see if I can find an identity that has cosecant squared minus 1. I've got this one that has cosecant squared, but it's not minus 1. But couldn't I modify this one? Subtract 1 from both sides, and then it would be cosecant squared minus 1. So for the sake of my notes, I'm going to come over here. I'm going to write down what's on my sheet. Now, you do not have to do this every time, but since this is our notes, my sheet says that 1 plus cotangent squared x is equal to cosecant squared x. I'm changing my thetas into x's. I know that I can modify that by subtracting 1 from both sides to get this. And so this thing that's in my problem can just be replaced with cotangent squared x. So that's going to be my first step. I'm going to leave this cosine squared x alone on the bottom and turn this into cotangent squared x on the top. That would be a Pythagorean identity. I got a feeling we can do better than this in terms of simplifying. Any thoughts about where to go next? I know what I would do. By the way, guys, I need you to keep in mind that I've probably done like 500 of these proofs in my career. Okay, so when you see me look at something and I'm like, oh, just try Pythagorean identity, it's not because like I'm like really gifted with proofs or anything. I've just done a whole bunch of them, right? Once you guys have done like a couple dozen, you're gonna start feeling really good about it too. But like I've done these a bunch, and every year I have to go back and redo them because you can't memorize your way through this. You got to think your way through it, but you do get better and better at it. So what are you guys thinking? I'm curious. What do you want to mess with next? The cosine squared or the cotangent squared? Cotangent squared. Do you want to try and use a Pythagorean, or do you want to try and do we could do a quotient? Reciprocal seems like it's not going to get us anywhere, but quotient maybe. Quotient, that's where I would be heading. Now this is going to get messy because we're going to have a fraction inside of a fraction. So when you do this, I need you to make it super clear to me as the reader, where's your main fraction bar? So I got my cosine squared x on the bottom. And then make sure that your fraction that's inside of your fraction is significantly smaller so that I can tell. Like, overdo it if you need to. Make sure that it's super, super clear to me. So this is going to be, I'm going to write cotangent as, it's cotangent squared, so that'd be cosine squared x over sine squared x. From here, I'm going to split off, and I want to show you two different ways of finishing this up. Two different methods. So here's my preferred one. Well, actually, it doesn't matter. They're both wonderful methods. They both work. I'm going to rewrite. This is called a compound fraction. Compound fraction, when you have a fraction inside of a fraction. You guys dealt with these last year in Algebra 2. Not to be confused with a compound fracture. You know what those are? That's when you break a bone, but it pokes out. Yeah, it's really gnarly, painful, painful, painful. These aren't nearly as bad. They're not super fun, but they're not as horrible. All right, compound fractions. One of the ways to deal with these is to multiply by fancy ones. That's my favorite way of dealing with them. Multiply by a fancy one. Cancel the denominators. I don't want this denominator sine squared x in there, so I know that if I multiply this whole fraction by a sine squared x, that's going to go away, right? So I'm going to multiply by a fancy one. It's going to be sine squared x over sine squared x. Okay, my whole purpose in doing that is to fix it so that my numerator up here, this fraction, cancels out, because sine squared times sine, this is sine squared on the bottom. I'm going to cancel. We're just going to be left with cosine squared x up there. Again, I do not want you crossing things out, but what we are doing, I'm going to do it very lightly, is that I'm canceling this with this. On the bottom, nothing is going to cancel. But can you kind of see what's going to happen next? Cosine squared is going to go away. Now it's just 1 over sine squared x, and then I think we can rewrite that as a single trigonometric function. That right there reminds me of my reciprocal identities. 1 over sine squared x is equal to cosecant squared x. This is usually how you'll see me work out problems with compound fractions. I tend to multiply by some fancy version of 1 to make the denominators I don't want go away. If you had Mr. Skaggs last year, and I can't remember if Mrs. You guys will have to let me know if Mrs. Malpass does it this way too. Mr. Skaggs likes to think of this as a fraction being divided by another fraction. If you think of this as cosine squared x over 1, that's a fraction being divided by another fraction, right? How do we divide fractions? Keep, change, flip. So I'm going to keep this one. It's going to stay cosine squared x over sine squared x. I'm going to change the division into a multiplication, and I'm going to flip the thing that I'm dividing by. All right, so we change division to multiplication, and we flip. Oops, nope. We flip the thing we're dividing by. And then we can see some stuff kind of canceling out here, cosine squared and cosine squared, and that leaves us with 1 over sine squared, which is cosecant squared x. So it gets us there a little bit quicker. They're both great. Whatever one is most familiar to you when you're dealing with compound fractions, either keep, change, flip, or multiply by a fancy one to get rid of your denominators. We doing okay? All right. I kind of built this up a lot. Is this like more or less intense than you were expecting? Is it less about this, or you were just like, yeah, I don't really know. That's fine. Okay. Let's try another one. We got 2 more to do here. Number 4. The reason, by the way, the reason that we're not doing the examples in the packet is that these problems can be pretty hard to gauge how much space they're going to take. Some people might do a problem in 10 steps and someone else might do it in 5 because they use different identities in a different order. There's no one right or wrong way to do it. Typically there's like a most simplified version, but I wouldn't worry too much about it. This is more to get us up to speed for proofs. So, all right, so let's start this off. We got sine of the opposite of x times the secant of pi over 2 minus x. And we're going to try and simplify this as much as possible. So, I'm already seeing 2 different possibilities for starting off. See 2 different categories of identities that we could jump into. See if you can identify 2 different possibilities. Now, we can't do 2 identities at the same time if they're in different categories. So we're going to have to choose one or the other. But can you identify the 2 that are available to us here? There may be more than that, but 2 that are really just screaming out at me. This negative x and this pi over 2 minus x are the things that I noticed right away. Anything with a negative x, I think about which category? Odd or even. So we could do odd or even here. Sine is, remind me, is sine odd or even? Sine is odd. So at some point, we're going to take this negative, we're going to pull it on the outside. Whether we do that first or second, we'll choose that in a second. But I also saw this pi over 2 minus x. That makes me think of what category? Cofunction. So we could turn this secant into a cosecant with just an x in it. Which one do you guys want to do first? The odd or even or the cofunction? Cofunction, you got it. So we'll leave this sine negative x alone, and we'll turn the secant into a cosecant. Not a cosine, cosecant. And that would just be an x then. By the way, if you had done the odd or even first, we're going to end up in the same spot in just a second anyways. So that would be cofunction identities, and now let's deal with the odd or even. So sine is odd, which means if there's a negative on the inside, we can pull it to the outside. All right, that already looks a lot simpler. I'm thinking about maybe trying to get everything in terms of sine and cosine and see if maybe something cancels or see if I can maybe get a tangent or a cotangent out of this. So cosecant we can turn into what? 1 over sine? Ooh, we're going to multiply sine by 1 over sine. I see what's going to happen here. What is the opposite of sine x times 1 over sine x? Those would cancel. -1. I don't think we're going to get any simpler than that. Hooray! Number 5. What do we got here? Sine x times tangent x plus cotangent x. Huh. Interesting. Anybody thinking about distributing? That kind of looks like a distribution type problem. So I could multiply this sine x by both of these things. That would be, might not be a bad idea for a first step. Anybody thinking about quotient identities? Maybe turn in the tangent and the cotangent and the sines and cosines? Yeah, well, yeah, I'd say those are probably our 2 key steps here. And I could maybe even not distribute here and deal with it. I can think of maybe 4 different pathways we can take here. So what do y'all want to do? Do you want to distribute or do you want to leave that sine x out there? You want to leave it? Okay, let's leave it and do our quotient identities. Now, these can both be turned into sines and cosines with quotient identities. I'm okay with you doing both of them at the same time. It's the same category of identity. So tangent is cosine over sine. Cotangent. I got that backwards. Darn it. Tangent is sine. I'm rusty. Cosine. And cotangent is cosine over sine. What to do from here? So I see a couple pathways going forward from here. One would be to distribute this sine x into both of these fractions and multiply them both by sine x. Nice thing is that would cancel this. This would just become cosine x, and this would become sine squared x over cosine x, and then we're going to have to deal somehow with that. The other thing, though, that I've seen, just from doing a million of these things, or 1,000 of them anyways, is we've got these 2 fractions here, and sometimes it's really useful to, if you've got fractions, to add them together and turn them into a single fraction by getting a common denominator. So that's another path we could take. So I was mentioning distribution, and a couple of you look like you weren't too keen on doing that. I saw some people shaking their heads. So why don't we try the common denominator thing here? Let's get a common denominator. So I'm going to set this up to get a common denominator. When I see this, I do want to see your thought process for this. So I want to see what fancy version of 1 are you multiplying each of these fractions by so that we end up with a common denominator. So this step needs to be explicit. I need to see what is this fancy one that you're multiplying by. So sometimes it helps me to think about what my common denominator is going to be. Once I do combine these 2 things together with a common denominator, what will my common denominator be? Ideas? This one's got a denominator of cosine x, and this one has a denominator of sine x. It's going to have a cosine x in it. It's also going to have a sine x in it. So I think cosine x, sine x, right? So I'm shooting to get a cosine x and a sine x in both denominators here. So what's this one missing? This one's got the cosine x already. It's going to need a sine x. So my fancy one here is sine x over sine x. This one has the sine x already. It just needs a cosine x. So this one will be cosine x over cosine x. So just double checking, are we good that we're going to end up with the common denominator of sine x cosine x? Numerator is going to end up, ooh, that's nice. Sine times sine is sine squared, plus cosine times cosine is cosine squared. It's my favorite one. Ooh, this is the first time this one's popped up. It's the best trig identity ever. Have you found it on your sheet yet? So I'm looking at the top of this fraction. I'm noticing we have squares now. Where do we look for squares in our identity sheet? Pythagorean. Do you see sine squared plus cosine squared in there? Heck yeah. Do you see why I'm so excited? What's it going to turn into? That's just a 1 up top there, right? I'm not even going to bother with the parentheses anymore. This is 1 over cosine x sine x. That's beautiful. And then this sine's going to cancel with this. At a certain point, you start seeing the end of the thing, right? You start being able to see a couple steps ahead. Can you see 2 steps ahead here? Can you see how the sine's going to cancel with the sine? You're going to end up 1 over cosine, and then you'll be able to turn that into 1 over cosine secant. So my next step would be 1 over cosine, and then secant. Oh, that was a fun one. I enjoyed that. I need to show you guys how we can check these in a moment, but I'm going to record that as a separate video because I forgot to do that for my first period class. Before we go into that, I need to talk about what's at the bottom of the page, but before we do that, I would love to answer any questions that you guys have at this point. After we've done 5 examples of simplifying using identities, any questions? Okay, I want to show you where we're headed. Where are we? Okay, so this is what we're going to give you a big old pep talk on Wednesday, but this is what we're going to be undoing on Wednesday. These are the 4 examples that we're going to do, and we're going to prove these. And it's going to be really similar. The difference will be instead of just getting that and being asked to simplify it, you're going to get that and be asked to turn it into this. Okay, so our goal will not be to simplify anymore. Our goal is going to be to turn it into something else. Now, sometimes the thing that you turn it into will be simpler than the original, but sometimes not. The nice thing is these are reversible. So if you don't like the idea of turning 2 cotangent secant x into this, that you could choose to start with this and try and turn it into this. All right, but it's basically going to follow the same format. You're going to start with this, you're going to write an equal sign, and you're going to have a column of stuff that's going to go down. The difference is we're not trying to make it as simple as possible anymore. We're trying to hit a specific target. Other than that, it's very similar to what we've done. So it gets a little bit trickier. And I like this simplifying because your goal is to just shrink it. Proofs get a little bit trickier because you're not always trying to simplify things. You really have to keep in mind, like, where am I trying to get and how can I head towards that? So I want to warn you that one of the things that is going to become very, very useful to us in the near future is being fluent in your binomial squared and difference of squared shortcuts. So I would encourage you to go through these. There's 10 problems here. Somehow I skipped number 9. My apologies. To go through these and work them out. Now, I don't want you to write this down, but I want to show you about how fast I would like to see you, okay? So if you'll look up here for a second, some of you are already working these out, but when you see something like x plus 5 quantity squared, I want you to be able to, about this quickly, be able to write out the answer. Please don't copy that down. I want you to go back and do that problem again yourself at some point. Something like this, I want you to be able to go, what is that, 4x squared minus 10 times 2 would be 20xy plus 25y squared. Something like this with a square root shouldn't be too terribly difficult for you. Multiplying two things that's a difference of squares should be really simple. Oh, look, those things are identical except one's a plus, one's a minus, so I can just do 6x squared, so that'd be 36x squared minus, and 1 times 1 is 1. That quickly to multiply those two things out. Because eventually you're going to be doing something like this, where it's cosine x plus 1, cosine x minus 1. And you're going to look at that and say, oh, that's just cosine squared x minus 1 squared. Cosine squared x minus 1. Same thing with something like this. Oh, this should have a square on it. I'm sorry, that's a typo. No, it shouldn't. We're factoring that. If I were to factor that, that's sine x plus 1, sine x minus 1. So I just want you guys to be familiar and comfortable with factoring and multiplying things out. I'd take a moment and run through there and make sure, I'll put answers up when we start in class. If you guys will remember, I'll give you answers to all these and you can check and see how you did on that. But I'm going to tell you, if it takes you more than 5 minutes to do these 10 problems, then you owe it to yourself to go ahead and do some extra practice and get better at dealing with these two things, okay? Because they're going to come up a lot, and you don't want to be stuck in the middle of a 15-step proof and having to go back and look up how to score a binomial, okay? Okay. Let me show you guys how to check these. So this is kind of our hint for how to do this. So I'm going to go back and check. Let's just check the last one that we did. You will be able to check your answers because I put the answers on the assignment. I also put some hints on the assignment.